O in the box?
It's the original energy.
Original energy?
The E sub zero?
Yeah.
Yeah.
Oh, that's 0?
That's a 0. Or O for original. Either way. So what happens if the total kinetic energy of a substance is 0? What are the particles doing?
Not moving.
Okay.
Completely frozen, 0 Kelvin.
And if we think back to that equation that we had up on the board, there we go. If kinetic energy is 0, then the temperature is 0. This is known as absolute 0. In theory, you can't get any less than that.
You can't even get that.
Well, and that's the third law of thermodynamics, is you'll never actually hit absolute 0.
They've gotten pretty damn close though.
They have.
Like negative 270 instead of 273.
Now, there are other definitions of temperature, in which case it is possible to have negative Kelvin. These are, to me, it's a semantics game, but to thermodynamics people, it matters. And even though, according to thermodynamics, you can never reach absolute 0, there's still people who try. They've got it down to the picokelvins for some things.
Down to what?
Picokelvin, 10 to the negative 12.
Yeah, yeah. They've gotten what down though?
Certain molecules down to that.
Of movement?
Yeah.
Jesus. Wonder when they'll meet Zepto.
Say it again.
So below Pico is Atto, then there's Yakuto, and then there's, no, sorry, it's Zepto, and then Yakuto.
I feel like you
Because
skipped
of course.
femto.
Huh?
Or is that the other direction?
Let me open my metric chart.
All right, and those are the 3 laws of thermodynamics. From that, you can develop an entire course in and of itself, but we will not do that because we have limited time. So let's talk about what happens when we put energy into a system. Well, actually, what happens when we put energy into a system? We'll start out with something fundamental. Pardon?
It remains as potential until you use it.
Not necessarily.
Well, to put energy into a system, you can either compress it or make it hotter. So it moves more. The molecules do.
So, when energy increases, entropy increases, is that what you said earlier?
When energy, say it again?
When energy increases, entropy increases, is that what you said earlier?
No, that entropy naturally will increase in a system. But if you want to reduce the entropy, statistically speaking, if you want to reduce the entropy, you will have to spend more energy than you will gain in the new system. All right, so if we have a change in energy, what, properly review for the test. If there's a change in energy, what are the things that can change?
It can either get faster or slower, get hotter or colder.
All right, so
or
change in
pressure, less
kinetic,
pressure.
change in kinetic energy. Everything you just described is changing kinetic
Yes, I know.
energy. Pardon?
I know.
Okay. What else could change?
The amount of power it will use once the potential energy is turned into kinetic.
Wow, you just skipped a step.
Yes, I usually do that.
Energy can be stored.
As,
Does the capacity have to get larger?
wait, sorry, Talon?
Usually has potential or something.
Yeah. So if there's a change in energy, there's either a change in kinetic energy or a change in potential energy. That's what I was going for, nothing too fancy. If I could change in kinetic energy, well, there's a possibility that there's going to be a change in temperature. But there could also be, and I think it's been hinted upon there could be a change in length.
Volume? A change in
Yeah,
volume?
so in dimensions.
Okay.
If there's a change in potential energy, well, we're dealing with storing things, so we could have, well, actually, mainly we see in thermodynamics, change in potential energy, we are dealing with a change in phase.
What's your name for the first law?
It's conservation of energy.
Okay.
So if I take an aluminum block that's been sitting in boiling water, I take the aluminum block, it's been sitting in there for, let's say, 10 minutes, so it's roughly the temperature is around 100 degrees Celsius. I take the block out, I put it on a table in the middle of the room. What's gonna happen?
Heat will transfer from the block to the table, possibly to burning said table, which is a chemical,
So it's going too far.
transformation.
Yep. Heat's gonna leave the block, there'll be heat transferred, or there'll be energy transferred into the environment. So energy is leaving the block, and it is cooling down. The question is, how does that relate? How does the energy leaving it relate to the temperature change in the block? Well, we have energy leaving it because there's a change in difference in temperature. What do you think it depends on?
Wait, what was the question?
The relationship between energy leaving the block and its change in temperature.
Heat transfer. Conduction.
What will it depend on in terms of the block?
Contact.
I mean, what it's touching?
Yes.
Let
That it's hotter or colder than the other thing.
me reword my question. I have an aluminum block and an iron block, both in boiling water. The same temperature, though they've been in there long enough that they're roughly 100 degrees Celsius. I take both of the blocks out, I suspend them in air in the table, in the room. Which one, or if the aluminum block loses 10 joules of energy and the iron block loses 10 joules of energy, still badly worded. What affects the relationship of the energy change and the change in temperature? That's ultimately what I'm going for.
Surrounding molecules.
That's going to affect the rate at which it changes.
Wait, are you talking about like if there was an aluminum and iron block and they both lost 10 joules of energy? Can you finish what the question was, even if it's badly worded? Because I don't know.
Which one would have lost more temperature? What's going to affect that?
Neither.
Isn't it like their boiling point?
Let's assume we are not dealing with changes in phase.
Oh,
Neither, because they're gonna end up transfer. If they're the same temperature to begin with, they're set on a table. They transfer heat. They're gonna end up, assuming that the table is 0 degrees. They're all gonna end up at 50.
But in this scenario, I've changed the amount of temperature I set the amount of energy loss to be the same for both. I could word it as, okay, I have two blocks roughly the same temperature, I stick them in the room, we come back the next day, and they are both room temperature. Which one lost more energy?
The aluminum one.
Why? What's gonna
No,
affect
wait,
that?
I lied. The iron one?
Why?
Okay, my issue is I'm still thinking of boiling point. Is that okay?
Yeah, I'm not sure that's the right tax.
Because one has a higher boiling point, meaning it has to have a higher, like it has more kinetic energy, I guess. And so if they both have to reach back to the same temperature, which is room temperature, then one of them would have to lose more energy than the other, since like if
But you're starting them at different temperatures then.
Well, so if both blocks are the same temperature and they're losing the same amount of energy at the same rate, wouldn't they just both cool down at the exact same time, same rate?
Yeah, but will they? I've done two scenarios here, so let's settle on a scenario. They start out at the same temperature, they end up at the same temperature.
Could you explain entropy
Which one?
to me? What is entropy?
Okay. Wow. Entropy is a measure of the order of things.
The order?
The order.
Like a hierarchy or like
As in
progression?
where things are.
So it's a
As
measure
of right
of.
now, all of you are sitting there. We can use entropy to come up with a measure for the order in which people are here.
So a measure of the order of things.
are we not supposed to use temperature in the answer more like that, having the dimensions?
Does the order is physical, right?
Oh, yeah.
Yes.
That does make sense, does it?
So what was that?
Okay, well, okay, I'm not the one who thought of this, but I think she's right. Well, okay, I
What did you
obviously,
say?
you obviously want us to use change of length or change of temperature in the answer. And,
We're concentrating on the change in temperature part.
well, basically she's just saying that because they both conduct heat differently, then it depends on their dimensions, their density, so.
No, I was just talking out loud and trying to say that it depends on the material itself, right?
All right, that's one thing there. It does depend upon the material. I'm gonna go ahead and put that piece up. Then it's the specific heat.
Do you put a degree mark on Kelvin? I don't think so.
Should not. Did I?
No.
It is material specific. All right,
How many variables are these?
well, one of them's gonna be changing temperature.
Yeah.
There's that last pesky little piece.
Moles.
No. Did you work that into it?
No, I'm just kidding. I was like,
If you did mole, you'd have to bring in another term.
oh my god.
Can you explain whatever's below the yellow line on the third law?
If there's a change in energy of a system, then there means there's a change in kinetic, which could be translated as change in temperature or change in size.
So change in energy in a system
Yeah,
can either be kinetic or potential. If
Yes.
it's kinetic, it's a change in temperature or the change in L, which
or
is
length. I was thinking one-dimensional, but length, surface area, volume.
volume. Okay.
So change in size.
So kinetic is temperature or volume, and right size is change in phase.
Is the last variable, is that like something we've talked about?
In this class, many times.
So does it work? Right?
No.
Okay. I give up. Energy. Many times? Time.
No, we're not dealing with how the rate at which it's changing. I'll spoil it. Mass.
Whatever.
I never said the blocks were the same size, the same mass, or any comparison of that. So we have this, and to me it almost rhymes, probably not to anyone else, but Q equals MC delta T. MC
Okay.
delta T, to me, there's a certain flow to that. But this deals with the energy transfer for something that has a change in temperature, not a change in phase. So specific heat, so let's take water for example. Specific heat of liquid water. Well, as with many things, they wanted to establish a convention that could be tested anywhere, or probably specifically anywhere within Europe, when they first established the convention, and it basically it's 1 gram per calorie degrees Celsius. So they established that as sort of the baseline. That is wrong. Those units are wrong.
Yeah, it is.
That's 1 calorie per gram degree Celsius. It goes backwards.
M and MC delta T, that's still mass
Yes.
of object
Wait, what does C stand?
or system. Mass of the object or
It's mass of whatever's losing the energy.
So specific heat equals 1 calorie per gram specific heat. For-
Just to give you some idea of the numbers. If we're talking about aluminum,
Oh, like how I would feel.
it's approximately actually metals in general are similar, but I'll just put down metal. Very roughly about 0.1 calorie per gram degree Celsius. So what this means is that the water takes 10 times more energy to lose temperature than the metal block.
Okay.
So if I take my really hot aluminum block and stick it into a cup of water at room temperature, the final temperature is going to be somewhere between the two initial temperatures, between the room temperature and whatever the block was. But will it be closer to the water or closer to the block, metal block?
The block.
Why?
I would just guess it. If he put a.
Abby?
The water, because the block is losing the heat into the water.
Oh, so you said the water is,
Temperature.
and Ram, you said block?
Yeah,
Why?
I was just guessing. But I just feel like, you're asking what the final temperature of the block would be, like, would it be closer to?
The final temperature of the system, because the block is gonna lose energy, the water's gonna gain energy.
Oh,
They're eventually going to reach some equilibrium temperature when they get into thermodynamic equilibrium. They'll reach some steady state temperature, assuming no loss to the environment.
mhm.
And is that final temperature closer to the water or closer to the block? The initial temperature of the water or initial temperature of the block? And Abby said
I
water.
changed the block.
I
But-
think
I
it's.
changed it to the block,
Oh, you're changing your mind? Okay, why the block?
because the water's gonna be, wait. Actually, the water's gonna be closer to the initial temperature of the block.
Is it because the heat transfer is coming from the block? So technically,
There's heat transfer out of one and into another, so.
exactly.
All right, so let's be more specific here. I got, let's say, an aluminum block. 5 grams, 25 grams of aluminum block at 100 degrees Celsius. I should have 25 grams of water at 20 degrees Celsius. I take my aluminum block, I put it into the water. I have a nice thermally insulated system, no energy is lost to the environment. And the final temperature, it's See, the midpoint is 60, so the final temperature, the question is it gonna be between 60 degrees Celsius and 100 degrees Celsius? Or is it gonna be between 20 degrees Celsius and 60 degrees Celsius?
The system. It's gonna be closer to the block.
So the final temperature is gonna be somewhere here. That's what you're saying.
Yes,
And why?
because, so
Why would you say such a thing?
honestly, I don't really know what the answer is, but I feel like I know what's going on behind the scenes. Like, so it goes from hot to cold. So obviously the aluminum is transferring energy out into the water, and that's heating up the water.
Yes.
And
And cooling down the block.
water, I would guess the water has a lower specific heat capacity or whatever. Is that what, does that come into?
Water has a higher specific, that's 1, and the aluminum block is around 0.1.
Oh, I'm sorry, I don't know that. Then, I think I take it back. I think it's I think it's the 20 to
Oh,
60.
they have the same change in temperature, right?
No. They have the same change in energy. Magnitude of change in energy, one's gaining, one's losing. But they will not have the same change in temperature. I will say, there's two choices. It's either gonna be closer to the water or closer to the block. We've nailed both of those. It is one of those two choices. So we've narrowed it down to 2.
Can you pull a
It's
second
the
one?
water, it's the water. I take it back. I think it's the water.
Do you have a reason for it or just gut?
No, so because isn't, wait, dang, okay, so technically, I think I'm misunderstanding this, but wouldn't there need to be more heat transferred from the aluminum block to the water to heat up the water? So
What?
that means the aluminum, even though it's at 100 degrees Celsius, which is really hot,